Well, hello friends. Welcome back to the program. Today we are going to continue working on our JIT compiler in libjs, and I'd like to get some actual JavaScript benchmark code running in the JIT. So today we are going to look at the Kraken benchmark, which is a classic JavaScript benchmark from Mozilla originally, and has a bunch of subtests here. Kraken is nice because the tests, they each take a couple of seconds to run. There's the older SunSpider benchmark, but we're already fast at that, so it's a bit less interesting. And Octane and Jetstream were a bit too slow still. So Kraken is a nice optimization target. So if we start alphabetically, we would begin with AI A star. So let's take a look at where we are right now with that one. If we just time it, and this is obnoxious, let me turn off the JIT completely just to get an idea of how fast it is today. This test runs in 6.5 seconds with, I guess I have some indexing running in CLion and so on, but it takes a couple of seconds, 6.5. So, and it's a fairly complex test. It's an implementation of the A star pathfinding algorithm, as far as I know. So today, I thought it would be really interesting if we could get some of this test compiling in the JIT. And when I say some, I mean some functions, because the way our JIT compiler works is kind of per function almost, really per bytecode executable. But every function creates a bytecode executable. So it kind of naturally, that's an easy way to think about it. And the first thing though, is that we need to do something about this. We can see here, JIT compilation failed for a function named neighbors, but it also failed earlier for neighbors and earlier. So we keep trying to compile the same functions over and over with the JIT. Even though it doesn't work, we keep trying again. So I thought that would be sort of the first thing we deal with today, is making one attempt per bytecode executable to JIT compile it. And if it doesn't work out, then we can stop trying. And likewise, if it does succeed, we keep the native executable that we got from the JIT. We keep that around cached so that we don't have to compile again if you call the same function multiple times. So the way we invoke the JIT compiler today is in the bytecode interpreter run and return frame, where we check, are we able to use the JIT compiler to compile this bytecode executable? If so, run the native executable. Otherwise, just fall back to running bytecode in the bytecode interpreter. So I think what we want to do here is we want to, I guess, like, move compilation into the bytecode executable and then have it maintain a cache there. It would be kind of a natural place to store it. So we could do something like executable dot get or compile native executable, something like that. Yeah. Something like that. And then we just need to go in bytecode executable. And let's have a private thing here so that we can transparently cache it. This is going to be a JIT native executable. Yeah, exactly. And then we should probably remember if we've tried to JIT or not so that we don't do it multiple times. Did try JITting. Let's try that, and I think we need to include ownputter, it sounded like down there, and actually we probably need JIT native executable as well. Okay, and then there's just the API that I invented, which was get or compile native executable. Sure, get or compile. It's kind of a variant of get or create, which is a pattern we use elsewhere. Get or create is pretty good. actually. We don't have to call it get or compile. Okay, so that would be native executable const get or create native executable, right? And what do? You get to kind of. Well, I guess what we want to do here is, like, if we haven't tried, if we didn't try JITting, then we want to JIT compiler compile this, which we need to include here. Okay. So, okay, this will take a little moment. Oh, shoot. We can't call run on native executables that are const. That feels like that should be allowed, because calling run doesn't mutate the native executable itself. So that seems like something that is logically const. Let's stick with that. Okay. And then once we've done this, I think that should be enough to at least reduce this spam here. And actually, once we get rid of the spam, we should be able to essentially get a list of functions that don't compile and the reason that they don't compile, which in all cases is going to be like, oh, you haven't implemented JIT compilation for this bytecode instruction. So trying that out, and indeed, compilation failed for all of these functions and the bytecode that we need to support in order to get it working. So that is a great first step. libjs JIT. What are we going to say here? I guess that don't keep trying to JIT bytecode executables unsupported. Bytecode executables. Instead, we now only attempt to JIT. We now only try JITting each bytecode executable once, then cache the result. The resulting native executable. Let's do that just to make it ultra clear what we're talking about. Okay. And actually, I think we only print out when something fails to compile. It would be kind of nice to print out when we succeed as well. Also, let's add some color to these things. It'd be nice to have a little bit of red here, and maybe after we succeed, we can do a little bit of green, let's say. JIT compilation succeeded. And yeah, turn off colors, and the name of the executable that we just compiled. Where are you? Bytecode executable name, right? Because here, if we manage to compile something in this file, we wouldn't even see it. Although it doesn't look like we succeeded. What if we do our little loop test? Yeah, so this is what it should look like, or rather, if we just send the assembly to dev null, this is what we should be seeing. JIT compilation succeeded for JIT.me. Okay, so now we're in pretty good shape to actually start chipping away at the unsupported bytecode ops here until one of these functions that goes all the way through the JIT. So print log both success and failure from the JIT compiler. These logs will eventually go away once the JIT compiler can always compile everything. But for now, they're useful. So, right. So I guess let's take a look at the things we have here. So we have type of variable, ResolveThisBinding, ToNumeric. These are just bytecode instructions, bytecode ops that we need to implement. ResolveThisBinding again, GetByValue, GetGlobal, NewArray. Okay, so that's a handful of things. Of course, there might be other ops in these functions that would prevent us from compiling. We only see the first one that causes us to bail out. So out of all of these, I feel like ToNumeric is really simple because that's just like a ECMAScript spec abstract operation for turning a value into a numeric value. And we really just want to call out to C++ for that one. And then in the future, we can do a fast path optimization just like we already do here in C++. If something is already a number, you don't need to do any of the conversion logic. But as we've been doing so far in this JIT compiler, let's just call out to C++, not worry too much about fast paths and optimizations at this stage. There will be ample time to do stuff like that later. So starting with ToNumeric, just put here, void compile ToNumeric. And what was that? Yeah, we'll just put it at the end here, I guess. ToNumeric, thank you, Copilot. Thank you, Copilot. Good boy. Okay, so then we want to have a C++ wrapper function for ToNumeric so that we can call this from our JITted code. That was generated beautifully. Really just calling ToNumeric on the value and then handling any exception here. And then we also need compile ToNumeric in compiler. Const ToNumeric operates on the accumulator, so it has no parameters in the bytecode instruction itself. And yeah, so load bytecode accumulator register into argument 1, make a native call to cxx ToNumeric, store the return value in the accumulator, and check for exceptions. Perfect. That is exactly what that thing should do. So let's see here. If we compile that, then ToNumeric gives way for some new things, I guess. What was it blocking before? It was blocking getStartingCell, function called getStartingCell, and init. Okay. GetStartingCell now wants GetByValue instead, and init wants GetByValue instead. Cool. All right, so we got ToNumeric out of the way. Let's see if we can just commit that. The JS JIT, implement compile. The ToNumeric bytecode instruction. Yes. I wonder how test.js is doing, by the way. It's very noisy. But interestingly, we are succeeding in calling some things. We're JITting some functions. We have one failure, so that'll be something to investigate later. But right now, we're just gonna plow ahead with the Kraken AI A* test here, because it would be so cool to actually get like a real JavaScript benchmark running in the JIT, even if just parts of it run in the JIT for now. All right, so let's do ResolveThisBinding, I guess. ResolveThisBinding really just wants to get you the value of the this keyword. So if you do like this in JavaScript, then this turns into a ResolveThisBinding bytecode instruction in our engine. So if you do like this.x, that's a ResolveThisBinding followed by a GetById with this value here as the base and this as the property. Anyway, ResolveThisBinding was used by a bunch of the functions, right? Yeah, so it's used by GraphNode, this anonymous function, whatever that is, and a couple others. So again, we're just going to call out to C++. Nothing exciting, but it's going to have to plow ahead with that anyway. Resolve this binding. I think a bunch of them are going to be like this. So compiler, compile, resolve this binding. Also, that works on the accumulator only as the implicit destination. So we want to make a C++ helper. Not quite. Binding, VM. I think actually has no arguments, yeah. But it can actually throw. There's some weird case where accessing this can throw. I forget what it is, but Alex was telling me a few weeks ago that there's some scenario where that happens. So we have to check for exceptions. Because this is a throwsy keyword. Okay, so here we just need to make the native call, I guess, actually. So native call to, call that function, and then take the return value, stash it into the accumulator, and check for exception. Cool. And then let's hook it up here so that we generate the code for it. Yep. And yep, thank you, Copilot. Very good boy. So used to having two terminals open when I do stuff like this. Okay, that compiled. Ooh, look at that. JIT compilation succeeded for something. Wonder for what? It's some anonymous function. Interesting. Wonder which one. How would we find out which anonymous one? I guess we know that it's somewhere between. So compilation is lazy. We JIT compile the first time you call a function. So we know that it happens sometimes between the first call to get starting cell and the first call to get ending cell is where we succeed. There's probably an easier way to figure this out, but like, whatever. Get starting cell. Where's the first call? There's only one call. Good. It's probably these two, which means it's probably something that's being called by get starting cell. So get starting cell calls is wall. What is wall? That's a field. Is that a function? Here. Graph node prototype is wall is the function. Ooh, look at that. That is exactly what I was describing earlier. So that's resolve this binding followed by GetById and then just returning that. Now we can totally compile that. So every is-wall is now going through the getting JITted into native code. That's so cool. And yeah, it'll be cached. Awesome. I don't think that's going to be enough to make the test faster, but it's pretty dang awesome that we actually have a piece of code in a real JavaScript benchmark being JITted. So let's commit here, libjs, JIT, compile the resolve this binding instruction. Cool. And then, you know, we can just keep chopping away at them like this. So GetByValue is pretty popular. Got a lot of functions blocked by that one. Same thing for GetGlobal. So I'm thinking let's do GetByValue maybe. GetByValue execute. Okay, so this one does a bunch of stuff. And oh, let me actually just tell you what that is. GetByValue is, we have two getBy that are important to know about. So this here is a GetById or identifier, and this here is a GetByValue. So the distinction is, in this case, we know already at parse time that you're accessing the foo field, right? Whereas with this kind of construct, foo is something that has to be computed at runtime. So it might say like a plus b, right? And we don't know at parse time what this is going to be. So it's a different type of operation. In the AST, it's a member expression with a computed property name, I think is the official name for it in the spec. Anyway, that turns into a GetByValue opcode. So we need to handle that. And we do that. This is what we do in the bytecode interpreter today. So I think we're just going to yoink all this stuff into a helper. And then we're going to put that helper into the common implementations file that I added in the previous video, just so that we can, actually, can we make that take a VM, I wonder? We're going to move it there so that we can call it both from the bytecode interpreter and from the JIT code. So VM, we already had VM, we need the, okay, so here we're going to take that as a parameter. Property key value, sure. And I think I would like to have the base before the property key. Maybe we just call them base and property. Or no, we don't have to get wild with renaming everything. Base value. I feel like it reads better if you have like O square bracket property key, then I feel like O, which is the base value, should come first here. Base object for get takes an interpreter. All right. Bytecode interpreter, fine. And I don't want to be assigning to the accumulator directly. I want to be returning this value here. So we can do that. And this fast path, by the way, is something that we can later learn how to do in assembly code. But as you can see, it's a little bit complicated. So we're going to need to, we're going to save this kind of stuff for later, because I don't want to bloat up the JIT right now with this type of stuff. Okay, and then I guess I need to extract the VM again, since I okay, so same thing here. Return string value rather than putting it in the accumulator, and same thing down here. Oh, wait. Now this guy can simply call GetByValue interpreter, and the wait, what's the base value? Was that in a register? mbase? Yeah, so let's also expose that while we're here, since we want to, we need to know the register from the JIT compiler so that we can actually fetch it. So the base is in a register in the GetByValue opcode, and the property is implicit in the accumulator. So let's see, GetByValue interpreter, and I want to pass in the mbase and also the accumulator. Wait, is that everything I need? Base value, interpreter, base value, property key value. Oh, I have to do that, I guess. And then I wanted to put that in the accumulator. Okay. Step 2, lift this, put it into the common implementations file. And take the function prototype, slap it up here, and we should be good. Let's see if that compiles. Seems fine. So that's step 1 is, what do we got here? libjs, bytecode, move, GetByValue implementation to common implementations. Sure. Because now we can call it from JIT code. So let's see, where's GetById? I'm going to put it right below him. GetByValue. Cool. And Thank you, Copilot. GetById, where are you? Here. ByValue. It'll be very similar to what we had with GetById, but it takes, yeah, just a base on the property. The property is a value. For GetById, the property is an identifier table index, since it's a known identifier. And here, this doesn't look entirely correct. So GetByValue needs to pass op.base. We need to fetch that VM register first, put that into argument 1. But properties in the accumulator, argument 2, call the C++ helper, put the return value from the helper into the accumulator, and check for exception. I think that should be good. Will it compile? Oh, look at it go. We probably need to turn this off now. So that is this thing right here. So if we succeed in JIT compilation, we will now run the native executable, and then after it runs, we print the contents of every local variable in the JIT executable that we just ran. And that gets a little bit noisy, so I'm going to do this so that we don't have to look at it. But we might need it later if we have run into some trouble. But that is pretty cool. We're now compiling whatever's down here. Very, very cool. Okay, so let's plow ahead. Let's just compile, or rather, let's commit here. So libjs JIT compile the GetByValue bytecode instruction. And then I see decrement right here in getEndingCell. That sounds really easy because we already have increment. So decrement is not going to be challenging. So we copy whatever we do for increment. Increment. Can you fill that in for me? Yes, you can. And increment is right here. So static value. Decrement, right, so decrement works the same as increment, just the other way around. Basically, ToNumeric on the value that we're going to decrement. If it is a number, just decrement 1, return it. If it's not a number, that means that it must be a big int, because after ToNumeric, it can only be either a number or a big int. So here we subtract 1 using big int primitives. That looks great. And we're calling it, has 1 parameter, just a value, putting the return value into the accumulator, checking exception. Perfect. I think that should be good as well. Let's see if we would be able to compile getEndingCell with that. Nope, not yet. Oh, because it does call. Ah. All right. Okay, calls are going to be a little complicated, so I don't want to dig into those just yet if we can avoid it. Compile the decrement bytecode instruction. Cool. All right, now what are we looking at? GetGlobal, blocking a couple of functions, 1, 2, 3 at least. Yep, and then we got PutById, call, type of, and new array. So how about we do GetGlobal? Should be pretty straightforward, I would hope. GetGlobal. GetGlobal is used for accessing a variable that we know statically must be a global variable. So our parser flags any variables that we can see, like, oh, this variable comes from the global context. And that means we can take a couple of shortcuts when fetching the value of that variable later on. Like we know that it can't possibly be a couple of edge cases. So we have to do less stuff to fetch it. So let's see. And we can also do inline caching of the global object shape. So that allows us to remember where in the global object it's stored. But one thing at a time. So first, we're probably going to need to expose these two. And the cache index for our inline cache, sure. And then execute does a whole bunch of stuff, which we are going to move to a helper. So GetGlobal, interpreter, and what do we need? We need, I guess we'll find out what we need when we try to do this. Just gonna yoink all of this, plop, yoink, and then this guy is simply going to get global. Okay, so what do we need here? We need a cache index. Sure, that's our U32 cache index. Got to pass that up. M cache index, sure. Inline caches are stored in the executable, actually. That's why they have indices. So every bytecode executable has a list of property lookup caches, global variable caches. That's their vectors. So the cache index is indexed into the inline cache array there in the executable. Okay, M identifier right here. It's going to be our identifier table index for the global. So we have to pass that. And I think that's going to be everything we need. Now we just need to fix it up so it, well, so it doesn't try to assign to the accumulator like that. Instead, just return the value. Likewise here, return, and wait, what's going on here? Set accumulator to undefined, set accumulator to result of this. Okay. Well, this, I guess we need to make sure that this uses that, but I don't think you need to do anything else. Arturo, auto value. So we do that and then return the value. Cool. I think that should be okay. Cool. And there we didn't throw, so return that. Oops. And then we just need to copy this to common implementations, or move it rather. Cool. GetGlobal, very cool. Okay, let's see if we can call that from compiled code. So GetGlobal. Cool. Put them here, maybe? No? Nah, that's not what I meant. Come on, dude. There we go. Okay, and then again, yet another C++ wrapper. Calling out to, no, this doesn't make any sense. Get global VM. We do have the identifier table index identifier, and we're gonna have the cache index. Yes. Yeah, exactly. This is what I want to do. Good boy, Copilot. So compile GetGlobal. Oh, did I not add that? Oh, I just call it GetGlobal. I bet you that's why things got confusing. Okay, so what do we do here? We have an identifier and a cache index. Both of those are JIT compile time constants because they're part of the GetGlobal instruction. So we just copy them into arg1 and arg2 as 64-bit constants. Looks fine. Call GetGlobal, return value to the accumulator, check for exception. Cool. Okay. So let's see if, oh, no, that didn't quite compile. Oh shoot, I forgot to check for errors here. Member access into incomplete type. So we need some includes. Anything else? Object and declarative environment as well. Is that it? That's it. Okay, still only compiling 2 functions, but at least GetGlobal is out of the way. So now we are blocked by type of still, PutById, call, and NewArray. All right. Should we do call or type of variable? Let's do PutById. Let's do PutById. So PutById, by the way, is the sibling operation of GetById. So this here is a GetById. This here is a PutById. So if you're reading something, reading the property, then you're doing a GetById. If you're assigning to it, that's a PutById. And of course, we had these. That's a GetByValue. And so consequently, this is a PutByValue. Make sense? Hope so. So let's implement PutById, since that was needed by it's needed by graph node. Okay, PutById. Compiler. Okay. Void compile PutById. Type PutById. Come on, dude. Okay. PutById. Actually, we need a C++ helper, as usual. PutById might become a little interesting because it actually has a lot of parameters. Yeah, exactly. It has tons of parameters. Has a base, property, which can't be an identifier, has to be a value. Then we have the value that we're going to put there. And then do we have a cache index for those? I don't think we cached those yet, actually. PutById. Yeah, they don't have a cache index, but they do have a property kind that we need to pass along. So first, let's just expose these so we can access them from the JIT. And then we need to take this stuff, and actually it's already separated into a helper function right here. PutByProperty key. So maybe we can just move that to the common implementations file. Already nicely factored. Yay. Okay. Property kind is not a thing. Because why? Property kind is, oh, it's in the op namespace. Okay, sure. So we just need to put a little bit of a op there and probably also include it. Sure. And then we also need ECMAScript function object. Sure. Anything else? No? You happy? Cool. PutByProperty key. Are you messing with the accumulator? Doesn't look like it. Nope, nope. That's good. So we can just put this in the in this file here as well, and then we should be able to call out to that. First, let's see that the bytecode engine still runs with this. Oh, shoot. PutById. I think it's fine. We'll discover if it's not. Just gonna commit this separately here. Wait. Oh crap! Did I not compile? I didn't commit GetGlobal. Okay, that's my bad. Let's see. So does this have GetGlobal also? Oops, oops, oops. Okay, I almost did a boo-boo here. Didn't separate my commits. All right, come on now. Let's do better. That one did need the environments, but not the op, right? Yep. And not that guy. Okay, okay. Okay, okay. Not you, but yes, you. That's the global, yeah. Not you, compile get global, not you. Oh, dang it, those are too close to each other. I'll have to yoink those out as well. So PutById. Okay, so we can add those. Get global, get global. Compile the get global instruction. Okay, we're making progress. Just one thing at a time. All right, and then let's get back on the horse with PutById there. So we put those back. Put this stuff back. There we go. Put that thing back. And is that good? Okay, so I think now we just need to call that. PutByProperty, which takes the VM, it takes the base, the property, the value, and what else did it take? It did take something more. I already forget what though. Property kind, right. Wait, so what on earth is going on here? Base, this value, value, property key. Ugh, and then kind. There's so much going on. PutById. Let's see what PutById does in the bytecode interpreter. So he calls it with base twice. At least that's nice. So we just have to pass the same. I think that's what we're supposed to use as the this value. Yeah, right. So if you access this inside the inside a put accessor for this setter accessor, then that's the this value that you would see. But for PutById, you always just see the base as this. So we can pass that twice, but name and kind. Okay, sure. So PutById is going to have, it's not PutByValue, so it does have identifier table index, property, and pass base value property. Was that it? PutByProperty key. Oh, property key. Oh, interesting. So how do I make one of those out of this thing? Right here. Sure, we can just do that. Okay. Property, sure. Yeah, I think that's okay. And we don't have a cache index. We have a bytecode op property kind to pass along. kind. You don't like it? Why don't you like it? Oh, because it doesn't return any value. Of course. So this is just void. Wait, what? Try or set exception. Has to be able to return something. Okay. I mean, we'll just cheat and do that. For now, that seems okay. Not the end of the world. So how do we compile this then? This is going to be harder. So yeah, we need to put by ID, but there are so many arguments. We haven't had this many arguments before. So let's see. arg1, that's the base, which we don't have in the accumulator, but rather in op base. arg2 is the identifier for the property. That one we have in property. And we need to raw value, which is in value. And it's not a VM register, it's a constant. So mov assembler operand register 2 operand im64. Okay, and then arg3 is going to be the value. So I think that's what's in the accumulator. Load VM register arg3. Can we get the accumulator? Yes. And then we have a property kind that we need to put in arg4, which is not a thing, but it can become a thing. You just have to add it. Not const eval. R8. That's not good. That clashes with our register array base. So we would clobber that if we use arg4. Crap. Okay, well, let's see. We have to put this on hold. And then we got to rearrange things here a little bit. So I think we can't be using R8 here. Let's see. The R8, R9, R10 is used also. So what if we just move these up to the very end of the register spectrum instead, like that? And now they are callee-saved. So we need to save and restore the callee-saved registers if we're going to mess with those. Okay, let's do that first. Okay, one thing at a time. Let's see. So when we enter arg4, where's arg4? No, when we enter in assembler, enter, right? So when we enter, let's before we do anything else, let's push callee-saved registers, and we can take care of that before we leave. Pop callee-saved registers. Yeah, stack frame is going to look a little wonky maybe, but let's not worry about that right now. Important thing is to just make sure that we don't clobber the callee-saved stuff, because that's our responsibility, and that's RBX and these guys. Yes. Pop callee-saved registers. Right. That all seems good, although that's an odd number of registers that we're pushing. Wait, what does that mean? That means that the adjustment here is gonna mess things up. Okay, what if I just push the same register twice? Let's just see that that works. At least then we get an even number of pushes and pops. Okay, so the JIT still works, still runs. This is just machine code to standard out. Don't worry about it. Yeah. Okay, so that part is good. We can push and pop the callee-saved registers. Fix me. Don't push RBX twice. Yeah, that's just a hack to get an even number right now, and I don't want to get stuck here thinking about the elegant solution for that. Save and restore callee-saved registers in JIT code. Sure. And then what did I want to do? I wanted to change the arg mappings so that we have arg4, which means I have to move these guys. So what was it, 13, 14, 15? Which should now be possible to just reroute them to there. Okay, that works. Okay, our program, our JIT code still works even though we rerouted the registers, and we're good boys and saving and restoring them. So that whoever called the native code that we generated wasn't like if the C++ code that was calling into the JIT code was using any of those registers, it wouldn't be cool for our JIT code to just step on them, right, and change their values. So we didn't save and restore those before because we didn't use any callee-saved registers, but now that we do, let's see, lib.js JIT remap, or move VM pointers into from R8, R9, R10 to R13, R14, R15. This way they don't clobber, they don't clash with the function argument registers. The sysv ABI function argument registers. Sure, cool. And once we've done that, we can add arg4, which means that we should be able to stash pop here. Oh, dang it. Maybe I needed to stash, wait. Yeah, there's the stash pop. Good, good, good. That's everything we had before, including arg4. Let's see if this works now. arg4. So 1, 2, 3, 4, passing everything to the PutById helper. Would you run? Not quite. Oh, wait, what? JIT assembler.h 152. Assertion failed. Because I'm doing a mov with some operand that I don't support in somewhere. Well, presumably in the code that we just added. Oh, it's probably this one here. Mov with im32. Oh, let's just use im64 for now. I'm not sweating the optimal instruction encodings. Like, we're generating instructions that could be way smaller, way more better packed with shorter forms. But we're not going to sweat that right now. That'll be plenty of time. And look at that. We have one more here. Is that the one? Or no? Wait, I forget. Did we get one more? I don't know anymore. Maybe we had 3 already. Did we have 3 already? No, we are getting one new one. It was init. Yeah. Look at that. We are now compiling init with the JIT as well. I wonder what that function does. Is this thing right here? Probably. Init, yeah. So it's like initializing a grid for the A* search. This can now run completely JITted. That's awesome. Okay, so let's commit here, libjs, JIT, support, compile the PutById bytecode instruction. Cool. What else do we got? We got NewObject. Does not sound terribly difficult, actually. What do we need to do for NewObject, I wonder? NewObject. NewObject should be dead easy. Because all it does is create a new object, a new empty object, and put it into the accumulator. So the equivalent JavaScript is literally that. This will produce a NewObject bytecode instruction. So that I think we can implement very, very easily. Let's do that and see. Next to new string here, maybe compile new object. Yes, new string. Let's do new object. Hello. All right, new string. As we can see, new string just creates a new string and returns it. Let's do the same thing for a new object. I guess we need the content. Oh, no. New object is what I'm trying to do. I already forgot what I wanted to do. Like that. And then the realm. What is the realm in this context? Probably just a VM current realm. Yeah, exactly. So we just do this. Realm is VM current realm. Cool. And then I think we can just return that. And this cannot throw, so it's not throwsy. We don't need to worry about it. Compiler, compile new object. Has no, instruction has no operands. Just stores the result in the accumulator. Can't throw exceptions, no need to check. Yeah. I think that's it, actually. Oh, check it out. Now we got one more. Graph node. I wonder if we're already faster at this point. Even though we're not compiling all of these, all of the benchmark, like we're failing because of call in a ton of places and new array. But it does start to feel a little bit like we are getting faster. JIT, compile the new object bytecode instruction. Let's see, if I just turn off a C-line here to make sure that we're not interfering with, because sometimes C-line indexing will run at like 1000% on every CPU. So we got OBS doing some business here, but even so, time.js, like that. Like, how long does it take? I wonder. 5.2 seconds. That's pretty interesting. What if we just build without the JIT? libjs, no JIT. Then what? 7.1. Look at that. So we're already getting much faster just from JIT compilation. Just like, as you've seen, we're basically just calling C++ and asking it to help us with stuff. We're not doing any fast paths in the generated assembly code today. Even so, it still gives us this much speed up because we no longer have to sit in the bytecode interpreter's execution loop where it's like fetching the next instruction, looking what kind of instruction it is, and like calling the handler and so on. And all of that stuff, we can just skip all that. here, and we're running sort of this pre-generated sequence of instructions instead. And the speed change just from that is substantial. It's amazing. And we're not JITting every function either. So if we, let's see, do that, we see that we're failing more than we're succeeding. So we still have many, many functions that we need to learn how to JIT. But we already got a bunch faster today. I wonder if we run some other test here, like from audio beat detection or whatever, see, we're succeeding for some things in there as well. Yeah, this is going to be a journey to support all of them. Imaging, darkroom, succeeding for clamp. Everybody else wants call. Yeah, function calls are going to be a little bit confusing, I guess, but I'm going to figure those out as well. Can I send that to dev null? No, I sent 2 to dev null. Nope, that's not what I wanted. Oh, this is terrible. Okay, never mind. Although it should finish fairly quickly. I just wanted to see that we haven't made a bigger mess. Still just the one failure. Okay, that's okay. That we had from the start. Okay. I kind of want to look at what doing call would entail. Let's see. Like, what would be the simplest way to do call? Let's take a look at the instruction. So call, execute, calls perform call after putting all the arguments in a marked vector. Perform call the helper. We can probably just yoink that out, actually. Maybe this isn't terribly hard. Cautiously optimistic. Let's have a look. Did I forget to commit? No. Okay, let's take a look if we can just implement a simple version of call here. Call type should be op call type. Sure. Outside of that, though, we should be in good shape. Of course, there will be like more powerful ways to implement call, but for now, I think we can do this. Oh, auto? Auto. That's interesting. What are we passing to that auto, I wonder? Perform call. Oh, they're passing themselves. Interesting. And then what does it do with the call? It checks this value and call type. Okay. So perform call is used by call and call with argument array. All right. I think we can solve this. So, okay. So those are moving to a separate function or separate file. We can handle that. Perform call, you moved. Common implementations. Yes, yes, yes. Right, undefined symbol. I would expect, because we don't have this version of it. If I have auto like that, can you instantiate that thing? I wonder. Also, this thing should return a value. So, okay, let's fix that. Value and instruction type, let's say. That can be const. Template, type name, instruction type. Because I want to instantiate the template twice. It's a little bit goofy, but whatever. And then we want to make sure that we return that. So not assigning to the accumulator, just returning it. And then how do I instantiate this guy? Like I forget the syntax. It's been so long. Instantiate the perform call for call and call with arguments array. I think that's what they were called. No, was it just argument array? Okay, my bad. Anyways, there we go. Okay, you don't like this because the way we're invoking it now doesn't make sense? Sure, so interpreter accumulator is try and return empty. Cool. That part is good. Okay, that compiles. Can we still run code? We can. Excellent. Lib.js bytecode. Move perform call helper to common implementations. Sure. And then we have a bunch of calls. We don't have a bunch of call with argument array. We have a bunch of call. And call needs to do this gunk right here, which throw if needed for call. Wait, why is that not part of? Oh, because it needs to happen earlier. Okay. I guess throw if needed for call should be in common implementations as well. We can deal with that. Call type op. Oh, that's another template situation. Template instruction type. Sure. We can do that. Yeah, this will be okay. Can you infer that I want to do this? Okay. Oh, what is throw type error for callee? Another helper. Anybody else using that? Okay, so you can come with us. Nice. You get to live here now. That's fine. Okay. Okay, we have successfully moved call and throw if needed for call. Lib.js bytecode move throw if needed for call helper to common implementations. That's not going to fit, but that does. Cool. Right. So back to the call instruction. This is what we need to do. This gunk right here. And we'll figure it out. And the compiler. How hard can it be? Compile call. Let's see, case, bytecode. Not quite. No. Compile call. There we go. Okay, now, it's gonna take some finessing, but we're going to want to call our little helper, cxx call that we need to invent. And that thing is going to do a bunch of stuff. Okay, so we need the callee, which is a value. And then we need to throw if needed for call with the bytecode interpreter. Sure. So try or set exception. and it returns if we set the exception. Yeah. It's good. And then we need the argument count. So that argument count is going to be a U32, I guess. U32 argument count, sure. Throw if needed for call. Oh, shoot. That thing wants something from the... It wants to know the call type. So maybe that thing should actually work in terms of call type instead. Or no, call is also passed here. Oh, dang it. Okay. It's a bunch of stuff going on there. Okay, maybe we leave this one as a fix me for now. Uncomment this and deal with it. Okay, so what does this thing do? So we have the arguments for the callee. We have them in a list, as I recall. Or how does that work? No, we have a first argument index. And then we have an argument count. And the argument indexes are just register indexes. So like, when you're calling a function, you have like all the arguments to the callee are sequential in registers. So like if the first argument register is 10, then the second argument is a register 11, and so on. So I guess we can be a little bit sneaky here and do this. And this. And then we will have the first argument index here, or first argument, yeah, like something like that. But I can't perform call without that thing. Okay, what did it want? It wanted, instead of passing the call, what do we take from the call? We take this value, we take the call type, and that's it. Okay, so what if we pass to this value in the call type? Okay, so this value and call type. You have to come with us. You no longer need to be templated. This value up call type. Sure. That seems very reasonable. So we just need to fix this thing up. So this value and my call type. All right. Once I do that, I just got to return this. Okay, perform call is bytecode interpreter with this value, the call type. Okay, we need a bit more stuff here. This value and the call type. Let's put them, I don't know, at the end maybe. This value, valid, bytecode, op, call type. Okay. Okay, so now we gotta pass all this gunk. So we have the callee, we have the first argument, what are you? You are a register, so you get to have the index there. Or wait, first argument, that's a constant. We don't want to load the register. We want to massembler mov. Okay, we want to load that as a constant into that register. Cool. And then we have the argument count. So that's another constant into argument 3, argument count, and then we have this value and call type. Okay, we're gonna get through this. The this value, what is the this value actually? This value is another register. Also, what's in the accumulator? I don't even know. Arg4 op this value. And then finally in arg5, we're going to put the call type. R9. Okay. Is that enough? Okay, let's see. I wonder if this will even work. It certainly compiles at least. Doesn't seem to have gotten any faster from it, but we're making calls now. Or maybe we're not making that many more calls actually, because we're failing in other stuff like not. But this should now compile actually. Our very first test program we should be able to compile the global context as well, because we have all these opcodes including call. So now we can compile the whole loop program, not just the JIT me function, but the whole thing. Yeah, and it works. Oh man, are we making calls? That's so cool. We are making calls. Awesome. My question remains though, what is the accumulator when you do a call? Maybe it didn't use, maybe call doesn't use the accumulator for anything. Huh. I would have thought the callee would be in the accumulator. Ah, whatever, it doesn't matter. Okay. So yeah, I'm just gonna you know what? Let's bring everything in here. Okay. Compile the call bytecode instruction. Yes. I left fix me about dealing with some throwsy cases. Yeah, we'll come back to that one eventually. But now I'm looking at this and I see like not feels like something we should be able to get out the way. All right, let's just look at not. What is not? Not is unary, I think. Not. Okay, so it's the unary ops. We don't have any of those, but we should be able to implement all of them in the same way, just like we do for binary ops. So let's take a quick look at that in the compiler. So for binary op, we have this. And for, let's do unary ops here. unary ops, compile, sure. This should give us a whole bunch more. Binary op. Okay, so this is how they're actually implemented for binary ops. So let's do unary. Okay, so wait. Messing that up. I wasn't supposed to be touching that code. I was supposed to be only doing these. Why don't you like that? I guess because they don't have an LHS. Is that why? We can't snake case name with 2 ops. So value, these would only have 1 input. Is that it? That looks better. What else is wrong? Let's look in the interpreter. How we do unary ops. Okay, so unary ops is just op snake case with the accumulator. Right. That's the whole thing. So when we compile those, we load the accumulator into arg1, call the cxx helper, put the return value into the accumulator, and check exception. Okay, why is that not good enough? Show me the error. Unused parameter op. Oh, okay. Fair enough. I don't need that. What else don't you like? Undeclared identifier not underscore. Ooh. Is that here? Not underscore? They are helpers here. Okay, sure. You boys get to move to the common implementations. Can you believe it? Okay, we take those, put them here. Very exciting. Okay. Oh, shoot. Now they would have to be bytecode : : wouldn't they? Ugh, that's annoying. Okay, wait, hold on. Let's not do that. And let's not do that. I'm just going to leave them. They're so small. You can barely notice them. So we just leave those guys here, and we take and put them in the compiler for now. That's okay. They're so small. You won't even notice them. Okay, so with those, look how much of it we're compiling now. It's getting more and more. Only 3 functions failing to compile? 4. That's awesome. JIT compile all the unary bytecode instructions. Unary means that it has 1 parameter, unlike a binary, which has 2. Or operand, not parameter. This is cool. So what about the other ones, like audio, beat detection? Yeah, we're definitely like starting to compile more of these things. Pretty interesting. What about crypto? I think I threw crypto at it last time and like nothing worked, of course. But see, now we can do some of it. That's pretty rad. Yeah, it's gonna be more work to get all these things working, obviously, but this is pretty satisfying. So I wonder, this crypto one in particular, let's see if we've made it faster. With the JIT, how long do you take? No JIT. Wait. What was it called? No JIT? 1.9 seconds with no JIT? Or no, maybe it's not stable. Just use hyperfine. Okay, so roughly 1.79 or 1.8 without the JIT. And with the JIT, a little bit faster. Not terribly much faster yet. So maybe we're not hitting all the interesting functions in this one. But I bet you as we improve this, we're probably going to see speed increases across the board. Anyways, I think maybe now is a good time to stop. But this is exciting. It's exciting to see more and more functions be JITable. So today was eventful. We got a whole bunch of things compiling. Now we can run partial JavaScript benchmark programs in the JIT, and they actually do run faster than they did before. So that's fantastic. If you made it this far, thank you so much for watching, for hanging out. I hope that you saw something interesting. I'm really enjoying this JIT series so far, and I think this is a whole new chapter in the Ladybird story in some ways that we can open here by starting to reach for higher and higher performance if we decide that we want to actually allow ourselves to do JIT compilation. And so far, it seems very manageable in terms of the complexity, and the benefits are high. I mean, even we saw today the increase from 7.5 to 5 point something seconds, or the speed increase here, substantial even without any particular optimizations. And the complexity cost is that we have to generate assembly, but the assembly we generate is really simple. Like, we haven't even tried to optimize it or do any fast paths. So it's interesting. It's interesting indeed. Anyways, we still have a lot of work to do, a lot of nooks and crannies to explore. So we'll be continuing with that. But for today, that's it. Thanks for hanging out. I will see you all next time. Bye.